Hello everyone, I am Biswaranjan Panda from Indian Institute of Science Education and Research, Barampur, and I am working on quantum information computing, and we have published a research paper. I think 8 months ago it was published, but we are working from 6 months ago from that, from the previous July 2022 we are working. Before that, I think January 2022. So the published link is here, it is given, you can see this, and we are the authors here, and this paper is on the means how to apply a Zidan quantum computing model in a robot, like how to control a robot, like any robot you can take, like classical robots. I'm not talking about quantum robots, it is all about classical robots, but the control procedure is based on quantum computing. So looking forward to this. We have our first slide, let's see. Yeah, so as you can see here, nowadays the quantum computing can be done by using several models. Like first model is like quantum circuit model. You can see in circuits, like classical circuits you can make, like AND gate, OR gate, like these gates. You can make this classical circuit like this, means like similar to this. We can use the quantum circuits. Like many types of gates are there: Pauli X gate, Y gate, Z gate, control node gate, U gate, like this. So many gates are there. By using this, we can make our quantum circuit model, right? Also, and another the second model is topological quantum model. These and the third is adiabatic quantum computing model, and another is quantum one-way quantum computing model. But we are talking about a recent model, which is called, you can see in the screen that a novel model was proposed based on the degree of entanglement. Degree of entanglement, it is called a concurrence value, right? So this model is recent, like 1 to 2 years back. This paper, original paper, was published. We have given the reference here, you can check here. The paper is this model is called Zidan's model of quantum computing, right? You can see in reference 3, we have can show you, okay. And in my research gate, you can see that present PPT, in that you can download there. So okay, and based on this model, you can see this is the name of this. And based on this model, we have some many algorithms are there, and many types of machine learning procedures are there in this model. We are going to second slide. Yeah. So what is entanglement? Nowadays, you know about entanglement because recently the Nobel Prize was given to this experimental part of entanglement. But the Zeringer, Ellen aspect, you know, this guys and closer. This they got this because of this entanglement violation of Bell inequality. You might have known this, but for completeness, I am saying that what is entanglement. So the entanglement is a, like mathematically, if you will say this, then if you cannot separate any two states by using tensor product, if you cannot separate, then it is called a entanglement state. Like we cannot say, like we can, but physically if we'll say this, then we cannot suppose we have a photon particle. Photon has spin 0. If we suppose if we are breaking it into spin minus half and plus half, two particles, okay, these two are entangled because if we will measure separately one in quantum, we call that superposition state. One particle is in superposition state, so a particle A and B are there. If we are measuring A state, before measuring it is in superposition state, but after measuring this, suppose it collapses to minus half, A collapse to minus half, then definitely we can say that B will means we will get plus half of that B state. Okay, so because of this entanglement, because this spin will be conserved, it is a photon particle, so spin is 0, so it should be conserved. So like this means explain we cannot explain one state without giving the idea of another state. It is called entanglement. So but what is the degree of entanglement? Degree of entanglement is like if the two particles are entangled, so we cannot say this that these two particles are maximally entangled or minimally entangled. Means like this, we cannot say by just looking this and two particles are there and we can see here two are entangled. Like, and we can say that these are entangled, but how much they are the strong bond there, like how strong the entangled is happened there. So this is determined by the degree of entanglement. Okay, so this procedure is used here in Zidan's quantum computing model. Okay, so we can say suppose we are taking a 2-qubit system, as you can see, that is psi E100 plus E201 and so on, E411. Okay, this is the 2-qubit state. So uh, so the concurrence value C, that is defined by 2 into mod of E1 into E4 minus E2 into E3. You can see in the screen. Yeah, okay, you can see. So the concurrence value is lies between 0 to 1. Okay, if it is if the concurrence value is 0, then no entanglement is there. If it is 1, then it is maximally entangled. Okay, so and suppose we are just excluding the if the middle states like E3, means suppose we are taking E2 equal to E3 equal to 0, then we can write that psi is equal to E100 plus E411. Okay, so then our concurrence value will again change. Then C is defined by 2 into E1 into E4. Okay, so we're going to next slide. So what is Zidan's quantum computing model? So the Zidan quantum computing model is based on, it is based on concurrence value. Okay, so the main operations are like proposed in Zidan quantum computing model is it is only the MZ operator. I'll show the figure. Yeah, you can, yeah, see this figure. Okay, so mainly we have to take GH, like 2 qubits are needed, and ancillary qubits that you can take according to your ancillary qubits, like according to your model, like whatever you are calculating or whatever you are doing, according to that you can take your ancillary qubits, but the 2 qubits of GH are needed there. And we will see the MZ, what is the work of MZ operator. Okay, so in the next slide I'm going there. Okay, so the MZ operator, Zidan's quantum computing model, we will see in figure here. Okay, the MZ operator have two parts. The first part you can see in the screen. Okay, the first part is here, that is entanglement creation. It will create the entanglement. Okay, and the another part is measuring the entanglement. Okay, means how means measuring the entanglement, degree of entanglement. How this is means by this formula, as you have seen. Okay, that C equal to 2 into U1 into E4. Okay, I have told you these two operators. First is to create the entanglement, and second is the to measure the entanglement. Two words are there. Okay. Now I'm going to this. Okay. So we have to implement this. Okay. MZ operator. So he gave two theorems are there. Okay. To implement the Giron's model. So we are taking two qubits, which is defined as U1. You can see here E1 00 plus E4 11, as we have defined before, and the quantum circuit shown in figure 3 is you can see used by measuring of the entanglement. We can get the value C. C is equal to 2 into P0011 to root. Okay, so we will get the value of P0011. How we will get this? We will get that 0011 amplitude of that 0011. Okay, the another thing is, see, C equal to 2 into root of P1100. Like this, we will take the amplitude of P1100, like not P1100, 1100. That amplitude is something that is P1100, and we have to take the root of that. Again, the another formula we can get, C is equal to root of 2 into P0011 plus 1100. Okay, so we will get this in a circuit model. How we'll implement this? See, here this circuit is. Here we are using cloning. Like, see, you know, the according to no cloning theorem, we cannot clone any type of qubit, but we cannot clone the arbitrary qubits. But here we know that GH are like control not get. So we just took again GH, which is again defined by control not get, because we need a 4 qubit system. You can see P0011, this is a 4 qubit system. Okay, so we'll go to next slide. That is theorem 2. Yeah, so theorem 2 is defined as, suppose we have given a unknown qubit, that is G, which is defined as E1 0 plus E4 1. Okay, where E1 and E4, okay, E1 and E4 goes to R plus real number plus basis. So the quantum circuit of this operator MZ, you have seen in figure 3, recognize the state of unknown qubit G. Okay, and the formula we are this theorem says that if P1111 is greater than P0000, if it happens, then the state qubit G we will get the G equal to E1 0 plus E4 1, which is defined as Z0 by n root 0 plus Z1 divided by n root 1. See, you can see this. Here is the formula. Okay, and we'll get where Z0 is defined as here. Okay, and also Z1 is defined as like this. We will get the solution by see, the proof is given in our paper. You can read this paper. No, Yeah, we have given this. Um, we have given this proof of this lemma theorem, and we will get this by solving a quadratic equation, not so complicated. It's easy thing. And the p 0 0 0 and the second is p 0 0 0 0 is greater than equal to p 1 1 1 1. Then the state of the qubit g is defined as this. Like before, it is defined. I mean, there are two possibilities are there. One is p 1111 is greater than p 0 0 0, and the second one is p 0 0 0 0 is greater than equal to p 1111. So there are two possible cases are there, and the according formula means the unknown state is defined as like this. Okay. Okay, so followed by this, we have given a lemma. This lemma is of theorem 2. It is given in our paper, and we have it is our original patent. So we have proved this lemma in our paper, but I am giving just a giving an idea about this. So we know that by normalization condition, if we are taking like suppose we are taking a qubit. Okay, here it is like this, that suppose we are taking a qubit that is g equal to one qubit g equal to alpha 0 0 plus beta 1 1. Okay, and alpha beta belongs to r plus. So okay, so we know that by normalization condition alpha square plus beta square equal to 1. By this we can get this, and another equation is defined in the theorem 2. Okay, so by implementing, by solving these, no, the second equation is, see, the first normalization equation is alpha square plus mod beta square equal to 1, and another is C is equal to 2 into alpha into beta. By using concurrence value, as you saw the formula in the initial, like in the first of the slide, sorry, second, I guess, yeah, second of the slide, that is 2 into e1 into e4. Here the coefficients are alpha and beta, so it is c equal to 2 into alpha and beta. And by using some simple algebra is there, a plus b whole square minus 4ab, no, a square plus b square equal to a plus b whole square minus 2ab, like this by using this formula you can easily get this formula. Okay. Mm, so the condition is, we know that two conditions are there. So p 0 0 0 0 is greater than p 1111. So for this, alpha is equal to 1 plus c root plus 1 minus c root, and beta is 1 plus c root minus 1 minus c root. Okay. Okay, so and the another condition is p 1111 is greater than p 0 0 0, then alpha is equal to 1 plus c root minus 1 minus c root, and beta is equal to 1 plus c root plus 1 minus c root. Yeah, so we have defined this lemma because we need alpha and beta value to calculate the concurrence value, as we have the formula c is equal to 2 into alpha and beta. So we need the concurrence value. So we have given the lemma, and in that in theorem 2 it is they calculated the alpha and beta, but it was somehow complicated by using by solving the quadratic equations and g z1 and the root of this, some stops are there, so complicated things are there. So we simplified this, and by using some means like algebra equation like a plus b whole square, some simple algebra, we can calculate this. Yeah. Okay, so the method, our aim is to control any kinds of robots, that is classical or any type of robot, anything, any type of robot. We have to control that robot by using quantum computing model. Okay, we have used this model because, as you know, the quantum computers are much faster by using because of this quantum mechanics principle, superposition, entanglement. These things are there. So here we are using quantum computing to control robots um, because we need see here suppose we have a million of words there for a robot. So if you will do this so see, you are using laptop, mobile, and so many things are there. These are you can say these are small computers. So if we will give a work task to a robot, if the robot is working million of works, so you can say, you can easily conclude, means see that it will be much slower. So as we know that the quantum computing is much faster than the classical computing, so we will use this here. And here you can take this you can you can control the movements of a robot like infinite times. You can you cannot give the infinite times works to a robot. So this procedure is much faster than the classical robot, classical control. Okay, not robot. Classical will control the classical robot. Okay, so first of all we'll use by using quantum teleportation. So suppose we are taking a robot in space. Okay, so we are using two qubits. One qubit is in the earth and one qubit is in the space. These two qubits are entangled, and we will use our degree of entanglement like concurrence value, and we will use this by our methodology. First, we will use our quantum teleportation. If you don't know the quantum teleportation, you can check in YouTube. This is easy thing. Okay, and the second is by using Zidan's quantum computing. Okay, Zidan's quantum computing, as we have discussed, we will create the entanglement and we will measure the entanglement. That degree of entanglement is called concurrence value. And here our proposed lemma, by using that proposed lemma. Okay, so the proposed lemma was our C value. Okay, the concurrence value. We have will calculate the value, that is C is equal to um, 2 into C is calculated there sorry, we will calculate the alpha beta. Okay, and the our proposed model is like we know that the our concurrence value is defined as 0 in between 0 to 1. 0 it's 0 and 1 itself also. Okay, and as we know, in the real number basis, in between 0 and 1 we will have infinite number of partitions in intervals we can take. So we just relate this formula by using tan theta. Okay, so we know that tan theta is equal to alpha by beta. So we can sorry, tan theta by 2. Okay, okay, we can write a qubit as sine theta by 2 plus cos theta by 2, sine theta by 2 0 plus cos theta by 2 1. From this we can calculate one formula, that is theta is equal to 2 tan inverse beta by alpha. So we need beta value and alpha value for using theta. We need, why we need theta? Because we implement our theta value in a unitary operator in our circuit. So in our circuit, as I have shown you, our C naught gates are there, and before that C naught gate, we will use our unitary operator U. In U, there are theta, phi, and lambda are there. Okay, so we will take the lambda value is 0 and phi value is 0, because phase and lambda will take 0 0, and we'll just vary the theta value. Our model is like that. I'll show you the table. Yeah, see, here is the table. So we have given a movement of four movements of the robot, and we have given eight movements of robot also in our paper. You can check there. So first of all, the forward, right, backward, and left. There are four movements are there, and we will define our concurrence value. You can just define our concurrence according to our random, like according to our benefits. Okay, so we just took the forward as 0 when the concurrence value is 0, then the robot will move forward, and when the concurrence value is in between 0 to 0.5, it will move right, and so on. Okay, so we just calculated the concurrence value as 0, 0.3, 0.8, 1, and the value of alpha for this is equal to 1, 0.98835, and so on, like this. Alpha by using that lemma. Okay, so so here we have run this our circuit in our IBM Quantum composer. There are two, one is simulator and one is system are there where we can run, and from this we got this. And see, in the second part of this table, the direction are there, the directions are there. Okay, sorry for the interruption. Yeah, the directions are there, that forward, right, backward, left. Then the interval, like angles are there, 0, 3, 0, 4, 6, 9 pi. We have calculated this. Okay, and as you can see here. Okay, these are the angles. Just look at this, and if you read our paper, then you will get the another example, that is 8 movements of this robot. We have divided our concurrence value into 8 parts, and we have done this. So by, as you can see, 8 parts, so we can use infinite number of parts. Okay, at last we just come to our advantages part. So the advantages, we can use it in space robot, and water research robot, like any type of classical robot, like hotel. You know that in hotels there are many types of robots are there. They are giving food to people. They can do multiple works at a time. They will cook there and give the food. So if they have a long hand like this, you can use. There are several applications are there, in that. Okay, we take millions of works in a single robot, so we don't need many robots out there. We can do multiple works by using single robot. So this is a great advantage of our quantum computing. Okay, so these are the references. As you can see, the main paper is this one, and our paper is this one. You can see this. Okay, and at last, thank you. Thanks a lot to listening my